Hello, and welcome to today's lesson on energy and power. Energy is the ability to do work or cause a change. Now, there are several different types of energy, but today we're going to focus on one, mechanical energy. Mechanical energy is the energy of position or motion. The energy of position is known as potential energy. And this is energy that's either stored because something is bent, like this arrow and bow. The arrow has stored energy because as soon as the man releases his fingers, the arrow will start moving. Or potential energy because of gravity, which is what this rock has because it has the ability to fall and create energy. The other type of energy is the energy of motion, which is kinetic energy. And anything that is moving has kinetic energy. First, we're going to look at an example of potential energy. So we're going to calculate the potential energy due to gravity that this rock has sitting on this ledge. So, gravitational potential energy is what is the energy that the rock has to fall. And it's calculated as the potential energy equals mass times the gravitational acceleration on Earth times height. Now, the gravitational acceleration on Earth is the same for all objects, 9.8 meters per second squared. So all we really have to do is plug that value in with our rock's mass and our rock's height. So that leaves us 50 kilograms, because our rock's mass is 50 kilograms, times the gravitational acceleration, 9.8, times the change in height. And this rock is 2 meters above the ground, so it would change 2 meters. So 50 times 9.8 times 2 gets us 980 joules, because our unit for energy is joules. So in calculating potential energy due to gravity, you need an object's mass and their height, and then multiply that by their acceleration due to gravity, 9.8 meters per second, and you're left with the object's gravitational potential energy. Now let's take a look at kinetic energy. Again, kinetic energy is moving objects. So we're going to look at an example of this moving biker. Well, kinetic energy is calculated by taking 1/2 times the mass of the moving object times its velocity squared. So if we use that equation for this example, we can see that the kinetic energy would be equal to 1/2 times the mass of the biker, which is 70 kilograms, times the velocity squared, which is 2 meters per second squared. Now, when you're calculating this, it's very important to do order of operations. So I suggest that you square this value before doing anything else. If we do that, we're left with 1/2 times 70 times 2 squared, which is 4. If we simplify this, we're left with 140, and don't forget our units, joules. So the kinetic energy of this biker is 140 joules. When we talk about energy, it's very important to realize that the total amount of energy cannot change. It must stay the same. You can't create energy and you can't destroy it. Which brings us to the conservation of energy law, which says energy may change form in a system, but the total amount of energy is always the same. And let's look at an example to get a better picture of this. Here we have a roller coaster. And you can see at the beginning, the roller coaster is not moving, the person sitting inside, ready to begin, atop a hill. So since he's not moving, his energy, kinetic energy, is 0. But since he has the potential to fall down on the track, they have 100 joules of potential energy. Now, as we go down, we can see that it changes. Because he starts moving, it changes from potential energy to kinetic energy, the energy of motion. But if we add it up, you can see the total amount does not change. We started with 100 joules of energy. As the person initially goes down, they have 50 joules of kinetic energy and 50 joules of potential energy, which again add up to 100. Now down at the bottom here, the person has 0 potential energy because they can't fall anymore because they're already on the ground. And here they have 100 joules of kinetic energy, which again totals up 100. And then as the roller coaster keeps going, they raise up, so their kinetic energy goes down, and their potential energy goes up. But again, the total amount of energy is still the 100 joules. So we can see that in the system, they change back and forth from potential energy to kinetic energy, but the total amount of energy always stays the same. In this example, it stays at 100 joules. Now that we've talked about energy, let's talk about power. Power is the rate at which you do work. And there are 2 ways we can calculate this. We can either use the equation power equals work divided by time, or we can use the equation that power equals energy divided by time. And the units we use when calculating power is watts and horsepower. Now, almost always use watts, named after a scientist, James Watt, who did the initial work of trying to quantify power. But in today's world, we still see horsepower used every so often in terms of motors. Because they produce a lot of power, we still use horsepower because watts is a very small number. In 1 horsepower, there is 745 watts of energy. And when you talk about motors that are 200 horsepower, it could be a lot of watts. So we still use horsepower for motors, but for our class, we're going to stick with watts. When you're trying to calculate power, the first thing you must do is try to decide which equation to use. Let's look at an example. Let's say you push a box 4 meters with a force of 12 newtons in 10 seconds. How much power is used? Well, in this case, it doesn't talk about energy, so we cannot use the energy equation. But it doesn't really talk about work either. But we can still use this equation because we can get work by force times distance. And we're given the force of 12 newtons and the distance of 4 meters. So if we plug that in, we're going to be left with 12 times 4. 12 times 4 equals 48 joules. Now, next step is to take that work and plug it into our power equation. So again, power equals work divided by time. So now we have our work, 48 joules, and we toss that over our time, which was 10 seconds, And 48 divided by 10 is 4.8. And our unit for this is, again, watts. Now let's look at another example. Let's say a machine uses 2,700 joules of energy in 30 seconds. What is the power it uses? Well, in this case, we're given energy and time, so we can use our energy and time equation. In this case, power equals energy divided by time. So we plug in our energy and our time, and we're left with 2,700 joules divided by 30 seconds. And if we put that in our calculator and find out the answer, we're left with 90 watts. Because again, our unit for power is watts. In conclusion, let's review. Today we talked about two different equations we can use to calculate power. Power equals work divided by time, or power equals energy divided by time. We talked about how energy in a system does not change. It can change back and forth between forms, but the total amount never changes. And lastly, we talked about how to calculate energy, whether it is potential, stored energy, or kinetic, the energy of movement. As always, if you have any questions, feel free to message me. Have a good night.